Hello everyone, welcome back. So in today's video, we're going to take up some problems from the check section of kinematics. So this is the first problem. Okay, so let's read the problem statement. So we have a 10-kilometer long straight road that connects two towns A and B. And now it's given that two cyclists start simultaneously, one from town A and the other from town B. On reaching the opposite town, a cyclist immediately returns to his starting town, whereas the other cyclist takes some rest and then returns to his starting town. Both of them can ride at a speed of 20 kmph in the absence of wind, but during their whole journey, uniform wind from town A to B increases speed of a cyclist going with the wind, and it decreases the speed of the cyclist that is going against the wind. Both the cyclists meet twice, first 2 kilometers and then 6 kilometers away from one of the towns. So in which town is the cyclist resting and for what period? Okay. So the question will become more clear when we draw a diagram. So first we have a straight road connecting two towns A and B, and the distance AB is given to be 10 kilometers. Now the wind flow direction is from town A to town B, and let's say the wind speed is U. So now the cyclists ride with a speed of 20 kilometers per hour, and again let's say it is equal to V. Now the guy riding from town A to town B will ride with a speed of U plus V because he is riding with the air, right? Okay, and this is just concepts of relative velocity, right? The wind speed direction and the riding direction is both the same, so we'll just add the velocities. And the guy who's riding against the wind stream will have a speed of V minus U. And so basically the guy riding from A to B will have a greater speed, right? Now it's given that they first meet at a distance of 2 kilometers from one of the towns. This one of the town that they're talking about will obviously be town B, because it's given that they meet at 2 kilometers from the town, right? So now obviously the first cyclist will cover a greater distance. So, okay, and the distance is going to be 10 minus 2 kilometers, which is 8 kilometers. So the town that they're talking about here is town B. Okay, so from this diagram we can easily get an idea of their speeds. They both meet at this particular point in the same time, right? So the first cyclist covered 4 times the distance covered by the second cyclist, which means the ratio of their speeds, which is V plus U upon V minus U, should also be equal to 4:1. Okay, same as the distance ratio. Okay, so now we'll substitute the value of V as 20 and we'll get the answer as 12 kilometers per hour. So now we know the speed with which the wind is flowing. So we can write down V plus U equals 32 kilometers per hour and V minus U is 8 kilometers per hour. Okay, so now guys, both the cyclists are at this location 1. So I'm drawing stick mans instead of the cycles. Okay, so now both the cycles are at this first meeting location. Now guys, this guy is running with a speed of 32 and this guy is running with a speed of 8 kilometers per hour. So the guy coming from the left only has to cover 2 kilometers more, right? So he's the first guy to reach town B and the second guy would still be somewhere over here. He still will have to cover some more distance to reach town A. Okay, so let's now figure out the time taken by the first cyclist to reach town B. So let's call that time as T1B, which is the time taken to go from 1 to B. So the distance is 2 kilometers and the speed with which he's running is 32 kmph. So he will cover it in 1/16 hours. So now as we know that their speed ratios is 4:1. So if the first guy covers 2 kilometers, then this guy in the same time will only be able to cover 1/4 of that distance, which is 2 by 4, which is 0.5 kilometers, right? So by the time the first rider reaches B, the second rider would have only covered 0.5 kilometers from 1, which means he's still at a distance of 7.5 kilometers from the town A. Okay, so when the first rider reaches B, this is the situation. Okay, so now it's given that one of these riders chill in a town for some time T. So let's say it's going to be this rider over here who already reached B, right? Because it looks like this guy has a lot of time to spend. So let's say he chills in town B for an additional time of delta T. Okay, now within this delta T time for which he chills, the other cyclist would have covered some distance, right? Now we don't know how much distance he actually covered. So let's do something else. So let's find out how much time does this rider take to reach town A. Now he has to cover a distance of 7.5 kilometers and his speed is 8 kilometers per hour. So let's call this location as location 2. So T2A is going to be 7.5 kilometers divided by the speed, which is 8 kmph. So this is the time which this guy takes to reach town A. And now he will immediately start cycling because this guy does not rest, right? And then it's given that they are going to meet at 6 kilometers from town B. For the second meeting, I'm drawing a different diagram. So let's say this is town A, this is town B. The second meeting will occur at a distance of 6 kilometers from town B, which means from town A, it is going to be at a distance of 4 kilometers. So this is where the second meeting will occur. Okay, so this guy, after reaching town A, has to cover 4 kilometers. But now the thing is, his speed is 32 kilometers per hour, right? Because he is traveling in the direction of the wind. Let's say this is point 3. So T from A to 3 is going to be equal to, he has to cover 4 kilometers with a speed of 32 kmph. Okay, and the cyclist who's at town B has to cover 6 kilometers with a speed of 8 kilometers per hour. So TB23 would be equal to 6 kilometers divided by 8 kmph. So now all we have to do is equate time after this particular instant over here. Okay, so let's talk about this rider first. So he stayed at town B for delta t time, and then in a time of TB3, he reached the point 3. So the total time elapsed for that guy is going to be delta t plus TB3. So now let's talk about the time elapsed by this rider. So in a time of T2A, he reaches town A, and after that, he takes a time TA3 to go from town A and reach point 3. So his time elapsed will be T2A plus TA3. Okay, so now all you have to do is substitute all these values in, and once you substitute, you'll get the answer as 18.75 minutes. So basically our first rider, he stays in town B for 18.75 minutes after reaching that town. So that's the answer to this question. Okay, so now let's move on to the next question. Okay guys, so this is question number 2. So imagine a change in the famous story of the hare and the tortoise. In this new story, when the hare wakes up, he finds the tortoise at 10 kilometers ahead, moving with a constant velocity. Okay, so let's just draw the diagram as we read the question. So let's say basically the hare is over here, and the turtle or the tortoise is at a distance of x0 in front of him. Okay, and it's given that the turtle is moving with some constant velocity. So let's just assume some velocities as well. So let's say the turtle's velocity is u, and the hare's speed is, let's say, going to be v. So the hare is not ready to give up and starts running again with a constant velocity. In its effort to win, it overcomes this distance in a time of t1. So basically the hare covers a distance of x0 in a time of t1. But during this time, the tortoise crawls further a distance of x1. So basically in a time of t1, the hare now reaches this point where the turtle was initially, but the turtle itself has crawled a distance of x1. So now this is the situation. So this was the situation at t equal to 0, and this is going to be the situation at t equal to t1. Okay. Now again the same pattern continues. The hare overcomes x1 in t2, but the tortoise crawls further a distance of x2. So we are getting an idea. So let's just copy paste this thing, right? Because the tortoise is slow. So this distance is going to be x2. And this is at time t equal to t2, and the pattern keeps on continuing. So as you can see, the separation between them keeps on reducing. And finally, after some time, the hare will be very close to the turtle. Okay. So now the question is, how long after the hare wakes up will it win? Now it's given that a monkey who has a referee measures only the distance x3, and he measures x3 and t7. So assuming the hare and the tortoise as particles, we have to find their speeds and how long after the hare wakes up will it win. Okay. I mean, I think this part should have been like, after how long will the hare catch up with the tortoise? Because we don't know where the finish line is, right? Okay, so first let's start writing some equations down. Now obviously guys, v is definitely greater than u, right? Hare is definitely faster than the turtle. So if you observe in a time of t1, hare covered a distance of x0. So I can say t1 is equal to x0 divided by v. And in the same time t1, the turtle covered a distance of x1. So this is also equal to x1 divided by u. So from here, actually we get x1 as u by v times x0. Okay. So now you can do the exact same thing for the second time period, right? So in another time of t2, the hare covered a distance of x1. And the turtle covered a distance of x2. And from here, you'll again get the same. The only difference is that the numbers will be added by 1. So from here, you'll get x2 equals u by v times x1. So now if you substitute for x1 in terms of x0, you'll get u by v the whole square times x0. So now u by v is a fraction, right? Because v is greater than u. So now from here, we can easily see the pattern. and we can write down xn as u by v to the power n times x naught. Now guys, xn is nothing but the separation between the turtle and the hare at time t equals to tn. So if you observe, this can only be 0 because that's what we want to find, right? We want to find the time at which they both come together. The separation between them becomes 0. That will only happen when n tends to infinity. Okay. Okay, so now let's take the help of these two informations. So x3 is going to be u by v cubed times x0. So let's substitute the values. Okay, so and after substituting the values, you'll get u by v is equal to 2 times 10 to the power minus 2. So now what is the relation for tn, right? When from t equal to 0 to t equal to t1, which basically means in a time span of t1, the turtle covered a distance of x1. Okay, so and in a time of t2, the turtle covered a distance of x2. So we can easily see a pattern here. So in a time of tn, the turtle will cover a distance of xn, which means tn is going to be xn divided by the turtle speed, which is u. Okay, now xn we can easily get from this relation. Okay, so t7 is going to be x7 divided by u, and x7 is nothing but u by v cubed, u by v to the power 7 times x naught, which is 10 kilometers, divided by the turtle speed u. Okay, so we finally have t7. Okay, so now this is given to be 1.28 times 10 to the power minus 7. So this, after solving, comes out to be 0.1 meter per second. So the turtle is moving at 0.1 meter per second speed. So this is going to be 2 by 100, which is 1 by 50. So the hare speed is 50 times the turtle speed. So the speed of the hare is going to be 5 meters per second. Okay, so we got v and u. Okay, so now we have to figure out when will the hare catch up with the turtle. So that will be basically, so that is simply t1 plus t2 plus t3, so on and so forth until tn, right? Okay, so t1 is going to be x1 divided by u, using this result over here, plus x2 by u, so on and so forth. So now this is going to be an infinite GP, guys. Okay, so this is the total time. Now here the common ratio of the GP is actually u by v, right? Now let's say I'm going to say this is equal to k for a second. So we can say x1 we can write it as kx naught divided by u, and x2 I can say it is k square x naught by u. So now we have to find the sum of infinite GP. So we can take k by u common, and this is going to be the first term x naught divided by 1 minus the common ratio, which is k. And once you solve it, the total time t turns out to be 2040.816 seconds. So this would be the solution to question 2. So now let's move on to question number 3. Okay, so in the third question, we have a train that is moving at a constant speed of 90 kmph on a straight level track. From the railway station P on the track, there is a village Q at a distance of y in a direction perpendicular to the track. Okay, so this is where the village is, and this is the railway station. And the distance PQ is given to be 1.2 kilometers. When the engine E is x kilometers away from the station, the driver honks a beep of horn for a duration of 44 seconds. Calculate durations of honking, tau P and tau Q heard at the station and in the village. Speed of sound in still air is C equals 350 meters per second, and there is no wind. Okay. Okay guys, so this is the engine of the train, and at this point there is a source of sound, basically a horn. Okay, when this distance PE becomes 1.6 kilometers, the driver starts honking, and he keeps honking for a time period of 44 seconds. So we want to figure out the time duration for which the villagers and the railway station people will hear the horn. Okay, so the distance PQ is given to be 1.2 kilometers. And the initial distance PE is given to be 1.6 kilometers. So this is similar to this is a similar triangle to the 3, 4, 5 triangle. So this distance is going to be 2 kilometers. Okay. So let's say this is instant t equal to 0 seconds. Okay. So here the driver just started honking. So the sound waves will take some finite amount of time to reach the village. And similarly, it will take some finite amount of time to reach the point P. Okay, so first let's figure out when will P and Q first hear the horn. So let's talk about Q first. So the sound wave has to cover a distance of 2 kilometers, and the speed of sound in still air is given to be 350 meters per second. So the villagers will first hear the horn after a time of 2000 divided by 350. So it has to cover 2000 meters with 350 meter per second speed. Okay, so let's just keep it as fractions for now. So basically, after the guy starts honking, the villager standing at Q will hear the horn after 40 by 7 seconds. Okay, so and similarly for the railway station, we can say it is equal to 1600 divided by 350, which is 32 by 7 seconds. Okay, so now let's talk about when the time in the clock will hit 44 seconds, because at this time the driver would stop honking, right? So by this time, the distance traveled by the train is equal to speed into time, right? So speed is 90 kmph multiplied by 5 by 18 to convert it into meter per second, multiplied by 44 seconds. This turns out to be 1100 meters, which is nothing but 1.1 kilometers. Okay, so basically in a time of 44 seconds, the train covers a distance of 1.1 kilometers, which means the distance between the station and the train will be 0.5 kilometers. So this is the station, this is the village, and this is the front of the engine. And this distance is 0.5 kilometers now. And this distance is anyway 1.2 kilometers. So this is the 5, 12, 13 triangle, right? So this will be 1.3 kilometers now. So the thing is, now at this point of time, driver has stopped honking, but the sound waves are still traveling through the air, right? So the villager will keep hearing the horn till the last sound wave, which is just released from the horn, reaches the village. After that point of time, the villager will stop hearing it. So now we have to figure out when will the last sound wave reach the point Q. Okay, so that time, let's say it is TQF. So this would be equal to 44 plus why? Because, okay, imagine we have a timer. Okay, so in the timer, it is showing 44 seconds. So, but the villager will hear the sound for some time greater than 44, right? So that's why I am adding 44 here. So this 44 plus 1.3 kilometers, which is 1300 divided by, so this is the final time on the clock till which the villager Q hears the sound wave. After this, the villagers don't hear anything. Okay, so similarly, the final time for the railway station will be 44 seconds, 500 meters divided by 350 meters per second. So basically, the villager will hear the horn from 40 by 7 seconds till this particular time, and the railway station will hear the horn from 32 by 7 seconds till this particular time. Okay, so all we have to do is take the difference of these two values to get the time duration for the horn. Okay, so once you take the difference, guys, TQ will turn out to be 42 seconds and TP will come out to be 40.86 seconds. Okay, so this is the time duration for which the village and the railway station hears the horn for. Okay, so now let's move on to the next question. Okay, guys, so this is question number 4. So we have a material point that is moving along a straight line. It enters a 87.5 meter segment with a speed of 5 meter per second, and it leaves with a speed of 10 meter per second. So the distance covered by the particle is 87.5 meters, and it enters with a speed of 5 meter per second, and it leaves with a speed of 10 meter per second. So now it's given that the particle crosses the segment with unidirectional acceleration. Now this is very important. The acceleration is only along one direction. So basically we cannot decelerate the particle. So we cannot hit the brakes. We have to keep hitting the accelerator. Okay. And it is also given that the acceleration never exceeds 1 meter per second square. Then we have to find the range of average acceleration of the point in this segment. So first of all, guys, the average acceleration is defined as the change in velocity divided by the time interval in which we are observing the change, right? Here the change in velocity by constraint, it is equal to 10 minus 5, which is 5 meter per second, divided by the delta t time. Okay, so here if you observe, the numerator is fixed. So we have to focus on the denominator. So let's name these 2 points as A and B. So we have to think of the situations in which the particle covers the distance AB the fastest and the slowest. If when it covers the distance AB the fastest possible way, its average acceleration is going to be maximum. So the corresponding to the T minimum case, the average acceleration is going to be maximum, and corresponding to the T maximum case, the average acceleration is going to be minimum. So now let's think about the situation in which the time taken would be minimum. Okay, so firstly, our constraint is that we enter with 5 and we have to leave with 10, and the distance that we have to cover is 87.5 meters. So that's the constraint. So basically we cannot exit with 9 meter per second or 11 meter per second. We have to exit with 10 meter per second. Okay, so the time taken will depend on the velocity, right? Imagine that we start from point A and we have to cover the distance AB in the minimum possible time, then obviously we would run as fast as we physically can, right? So basically what we'll do is we'll hit full throttle on the accelerator and we'll quickly rise our speed from 5 to 10 meter per second. And after this point, we'll keep the velocity constant. Okay. So again, remember guys, we can only accelerate. We cannot hit the brakes, right? So after reaching 10 meter per second, we cannot accelerate anymore. We have to move with constant speed. So this is the condition in which the time taken would be minimum. So we can think of it with the help of a VT diagram. So at time t equal to 0, the speed of the particle was 5 meter per second. So this is 5, this will be 10. We want to make it reach max speed as soon as possible, which means the acceleration should be maximum. Basically, we have to hit full throttle on the accelerator, right? And the maximum allowed acceleration is 1 meter per second square. So the angle it makes with the horizontal is 45 degrees, right? Now the height of this triangle is 5 units. So the base is also 5 units. So the corresponding time is going to be 5 seconds. Okay, so we'll hit the accelerator for the first 5 seconds. And after that, we'll maintain the speed. We'll maintain the speed constantly at 10 meter per second till the distance of 87.5 meters is covered. Okay, so let's say that time is covered. So let's say the time taken to cover that distance is going to be t. Okay, so we want to figure out this time t. This is also the minimum time taken, right? So let's just write it as t min. Okay, so now all we have to do is make sure that the area under the curve is equal to 87.5 meters, because the area under VT curve is the distance, right? Or the displacement. So basically this is actually a half trapezium, right? So the area is going to be half times the height, which is 5 seconds, times the sum of parallel sides, which is 5 plus 10. And this would be a rectangle whose base is t minus 5 and the height is 10. And this should be equal to 87.5 meters. And this after solving comes out to be 10 seconds. So the t minimum comes out to be 10 seconds. Okay, so if you substitute 10 seconds over there, the max value of the average acceleration will come out to be 0.5 meters per second square. Now in the minimum acceleration case, again, we need to make sure that we cover the distance AB the slowest. So if you want to cover the distance AB the slowest, then we have to walk very slow, right? Now as the slowest that we can walk is 5 meter per second, right? So what we'll do is we'll walk with 5 meter per second for the maximum possible allowed time. And then we'll quickly raise our speed to 10 meter per second. So this way the time taken will be maximum. So the goal is to walk for the maximum amount of time and then run. Now we figured out from here that if we want to accelerate from 5 to 10 with an acceleration of 1 meter per second square, it'll take us 5 seconds. So basically in the last 5 seconds of our journey, we'll hit the accelerator, but before that we'll travel with constant speed. Okay, so now we can also use the kinematics formulas, right? So we know for the last 5 seconds, the acceleration is 1 meters per second square and the initial speed is 5 meters per second and finally it is 10 meter per second square. So we can use s equal to ut plus half at square and find out the distance, right? 5 into 5 plus half into 1 into 5 squared. So this is 25 plus 12.5, which is 37.5 meters. So in the last 5 seconds, we would have to cover. So from the 37.5 meter mark, we need to start accelerating. Till then, we will move with 5 meter per second. So this distance is going to be 87.5 minus 37.5, which is 50 meters. Okay, and the time it takes to cover 50 with 5 meter per second is 10 seconds. So the T max case, so the T maximum is going to be the 10 seconds to cover the 50 meters plus the last 5 seconds to cover the 37.5 meters. So this comes out to be 15 seconds. So the minimum value of the average acceleration would be equal to 5 divided by 15, which is 1 by 3 or 0.33 meters per second square. So the range of the average acceleration is going to be 0.33 to 0.5, and obviously there will be equality, right? And the equality signifying the extreme cases that we discussed. Okay, so yeah, that was the answer to this question. So now let's move to the next question. Okay, so this is a question from free fall. So this is question number 5, and we have 2 balls that are dropped from the top of a cliff at a time interval of 2 seconds. Okay, so first we drop a ball, and after 2 seconds has passed, we drop the second ball. The first ball hits the ground, rebounds elastically, reversing direction instantly without losing its speed, and collides with the second ball at a height of 55 meters from the ground. How high is the top of the cliff? Okay guys, so let's take 2 balls, one green ball and one blue ball. Okay, so let's say we drop the blue ball first. We are holding the green ball on our hands and we have dropped the blue ball. So now the thing is, it'll go hit the ground, rebound with some velocity, And finally, when it is at a height of 55 meters, the green ball collides with the ball. So this is what is given to us in the question. Okay guys, so now the thing is, this question can be done very easily if you observe it for some time. Okay, so first let's do the height marking. So the collision happens at a distance of 55 meters from the ground, and let's say this distance is d. So d plus 55 is the height of the cliff. Okay, so now observe something, guys. If the time taken for the blue ball to cover a distance of d is the same time taken by the green ball to cover a distance of d, right? Because both of them have the same acceleration and 0 initial velocity. The motion is about to start, so the clock hits t equal to 0 seconds and the blue ball is dropped. Now, when the blue ball has fallen by a distance of d, the time on the clock is time t equal to t1. So basically in t1 time, the ball has fallen by a distance of d. Now I'm drawing it over here. Okay, again the motion continues. The ball will hit the ground, come back, and when it comes back, it will collide with the green ball, right? And now let's say the time on the clock is t equal to t3. So basically the time it took for the ball to go hit the ground and come back is t3 minus t1. Okay, and now in this time, the green ball will obviously descend by the height d. Now how much time did the green ball take to fall by a distance of d? It will be equal to t1. Right? Because that's the time the blue ball took to fall by a distance of d. It's the same time that the green ball will take as well. Okay, but the thing is, the green ball was being held for 2 seconds before being dropped. So now all we have to do is equate the times. So after the clock started, the green ball first of all was being held for 2 seconds, and then it took a time of t1 to fall by a distance of d. And now the blue ball, okay guys, so instead of writing t3, what we should do is the time it takes to fall by a distance of d is actually equal to t1. So let's write that down. And then after reaching this point, let's say the time it takes to hit the ground and then come back is actually delta t. So let's just do this. So this t1 plus delta t is the time elapsed. So again, the blue ball took a time of t1 to drop to a height of d, and then it hit the ground and came back. And for that, the time taken was delta t. So these two times have to be equal, right? And from here, if you observe, t1 cancels out and we get delta t equal to 2 seconds. So in short, basically, if both of them were left at the same time, they both would fall by the same distance d in a time of t1, right? As the green ball was being held for 2 seconds, the blue ball got an extra time of 2 seconds to cover this distance. Now it's pretty simple. So the time taken by the blue ball to hit the ground and come back is 2 seconds. So the time it takes to reach the ground is going to be half of it, which is 1 second. So in a time of 1 second, it covers a distance of 55 meters. So we can use s equals ut plus half at square. So we can say 55 is going to be the initial speed u. Okay, so here let's assume the speed is u, okay, times 1 second plus half into 10 times 1 square. And from here, u just comes out to be 50 meters per second. Now guys, if the velocity is 50 meter per second, then basically from the dropping point, a time of 5 seconds has passed, right? So t1 is nothing but 5 seconds. So now this distance, which is basically d, is nothing but half into g into 5 squared, which is 25. So this comes out to be 125 meters. So now the height of the cliff is nothing but is going to be 125 plus 55, which is 180 meters. Okay, so that was it for this question. So all we had to do is identify the fact that the extra time delta t would be the time taken by the blue ball to go hit the ground and come back. Okay, so yeah, that was this question. So yeah guys, so that was it for this video. If you guys enjoyed the video, please do like, share and subscribe. And yeah, that's it. Thanks for watching.